Welcome to this session. This is session 2AH. The presentation is pre-recorded by my friend and colleague Jim D of BMC Software, who also sponsored this particular session. It's pre-recorded. He'll be talking about squeeze your data with DB2. It's a learner session for compression. So if you're a 101 attendee, then this will be right up your street. But if you've been in DB2 for more than that, then it is probably going to be a very good refresher, and you will learn things that you didn't know, I'm sure. So I will hand over. There's no waiting room, so people can join in straight away. I'll hand over to the recording, so enjoy. There will be opportunity for questions. Jim actually may dial in towards the end of the presentation. I mean, it's like 5:30 in the morning for him in Austin, in Texas. So if he's unable, please type in your messages, your comments in the chat, and I will forward them on to Jim, and Jim has promised that he will answer them personally by email. So without further ado, I will hand you over to Jim D.
Well, good afternoon, good morning, good evening. Thank you so much for inviting me to speak at the GSE UK this year. It's an honor, and I always enjoy it. I wish I was there in person, but you know, we do what we can. This is session 2AH on the DB2 track, labeled Squeeze Your Data with DB2. My name is Jim D, and I work for R&D and at BMC Software. So what I'm going to be talking about today is the history of compression in DB2. This is meant to be a beginner's level presentation, but I'm hoping anyone, even those with some experience, will find something interesting while we go through this. As you'll see, compression's been around a long time, but continues to evolve. The most recent changes have been to DB2 12 very recently. Here's our agenda for the day. I'm going to give a short introduction, talk a little bit about what compression is, why it's important, and why your applications might want to exploit it, just in general. Then we'll talk a 1 or 2 slides on a little bit of history, but then get right into talking about table space compression, the one that we've all been familiar with since version 3, and some of its implications for performance. Then I want to get into index compression, how it differs from table space compression, and what it implies for application performance. Then we'll take a look at lob compression. And finally, end up talking about Huffman, which is a very recent change, as I said, made version 12 of DB2. As you can see, there are several flavors of compression in DB2. And one reason I did this presentation was to answer some confusion I'd heard from fairly experienced people in some cases about how the compressions are the same or not and how they work. And we'll see that there's a wide variety of implementation techniques, operational constraints, and application performance implications. So let's go back for a little basic history. Those of you who read Robert Heinlein when they were younger, as I did, will be familiar with Tonstoffel. It was a phrase Heinlein came up with. It said, "There ain't no such thing as a free lunch." And basically the philosophy is there's always a cost associated with any benefit, and disk compression is certainly an example of that. We can see here that the general idea is to reduce your disk costs by shrinking the size of your disk data files. So the green on the left has been shrunk by about 50%, as has the blue before being stored on disk. In almost all cases, in all cases, actually, there is some kind of trade-off involved. You can save disk space, but you're going to end up using other resources to do it. Usually CPU, sometimes storage, real storage or virtual storage in the address spaces that run your applications and DB2 itself. And sometimes in the performance of the applications. And we'll try and delve into that a little bit as we look through. Before I start talking about compression as part of the DB2 engine, let's go back into the deep mists of antiquity in the mid 80s, late 80s, when there were no tools available, no compression available as part of the DB2 engine. What could people do who wanted to save on disk space? And one common response was to use the edit proc capability. The edit proc is an exit that gets invoked each time a row is examined, inserted, or updated. And the idea is to compress each row before you put it into the buffer pool, and then to expand it as it comes out of the buffer pool. So you can see the edit proc fitting between the buffer pool and the rows being selected or even inserted, is selected from the table or inserted into the table. So at the top, you're seeing the green, yellow, and blue rows being extracted from disk and expanded before they're returned to the select. On the other side of the equation, when you do an insert or an update or the load utility, each row is compressed by the edit proc before it's written to disk, before it's written to the buffer pool, excuse me. The main problem with this was performance. For every row accessed or updated, the exit had to be invoked by DB2 with all the overhead that implied. You had to find the exit code, load it, and then branch to it. The exit code also had to execute a compression algorithm with minimal hardware assistance. Compression is relatively cheap. Decompression or expansion of the rows is can be very expensive depending upon the algorithm you use. So the reason for this diagram is to introduce some of the concepts and talk about, start discussing some of the trade-offs involved with various techniques of compression and expansion. Edit procs never really caught on. There are probably a few people listening to me who remember working on them or using them, but by and large, it wasn't a good solution to saving disk space. Then IBM came out with version 3 of DB2. Now, this diagram looks very similar to the past one, and there's a reason for that. Obviously, if you're compressing table space rows by whatever method, at a high enough level, the basic operation is going to look very similar. But there are some significant differences here. As with the edit proc exit, the idea is to compress each row of the table as it's inserted or updated in a page image in the buffer pool, and then to expand it again as you read them via select. Notice that as well as an insert or update, the load or reorg utilities can also invoke compression. So there are a couple of significant differences about this and the edit proc we saw in the previous diagram. First of all, the code for compression and expansion is in the DB2 engine itself. So there was no overhead associated with loading and calling a piece of application or exit code. The other advantage is that IBM exploited a hardware instruction, the CMPSC, which actually allows for hardware compression. It's an expensive instruction as instructions go, but a lot cheaper than writing compression and decompression algorithms in software. The CMPSC instruction depends upon a dictionary which relates strings found in the table rows to shorter strings that can be used to indicate those. And that's basically how the compression works, implementing a libsimple algorithm. The dictionary is created during execution of the load or the reorg utility, and a copy of the dictionary is stored on disk as part of the table. So we'll take a look in the next slide. We'll talk more about the dictionary and how it comes about in the next slide. This has been a very popular feature of DB2. Usually at this point, if I'm presenting live, I ask the audience how many people use table space compression. And typically, almost every hand in the room goes up. So most of your data is being compressed. The reason for that is that 85% compression ratios are fairly easy to achieve. 50 is probably the minimum for any reasonable production data. And the CPU overhead is minimal. In fact, some cases, you can find your application performance improving. So it's pretty much a no-brainer feature to use. And as I said, most people typically use it. So I said I'd talk a little bit more about the dictionary. And we saw on the previous slide that the dictionary pages have to be stored with the rest of the pages of the table. And this is how the load utility arranges to do that. The first thing it does, writing an image of each page of the table into the buffer pool, is to write a few overhead pages. They're very important, but have nothing to do with compression. So that's all I'm going to say about them here. Then look at number 2 in the diagram. The load utility starts writing uncompressed rows to the first data pages of the table. As it's doing that, it's building a dictionary in memory from the uncompressed data. And that's the third operation referred to. When enough data has been loaded to allow a good dictionary for later compression use, the dictionary is hardened onto page images and written out to the disk. And actually, the dictionary pages occur before the data pages, as you can see. From that point on, the load utility uses the dictionary to compress each row, so all the rest of the rows are compressed. I haven't shown the reorg utility here, but it works in quite a similar way with one significant difference. Because you have access to all of the uncompressed rows during the unload phase, before the reload phase starts, the reorg is actually able to write all the dictionary pages and compress all the data rows. So you typically find in production level data a slight increase in efficiency in compression from reorg as opposed to load. I referred to the table space in this diagram, but it could actually be a partition of a partition space or a partition of a PBR. Each partition of a PBG has its own dictionary, but those are typically very similar because the data has the same characteristics in all partitions. So how can you look at compression and start to evaluate how effective it might be for a particular table? And with this slide, I'm going to introduce the DSN1 comp utility. It's a standalone utility like DSN1 print or DSN1 log P that allows you to include in the syshut1 DD the VSAM files for the table space you want to analyze. And you can see here, I've included that as syshut1. This JCL that I'm showing would actually run against the table space. In practice, you probably wouldn't want to do that. You would want to run against an image copy of a production space to avoid the outage necessary to deallocate the actual table space from your production DB2. If you do that, you need to specify parm equals full copy in your on the exec statement of the JCL. So let's take a look in the next couple of slides what you see out of the DSN1 comp utility. And there's a fair amount of DSN1 comp output in this presentation, and I apologize for reformatting it, but I haven't changed any of the essential data. So in this case, it's telling us that hardware support for Huffman compression is available. So I ran this on a fairly recent version of function level of DB2. And I'll talk much more about Huffman compression and choices associated with that later. In this case, I was only interested in getting fixed compression numbers. So that's what we're going to look at. So basically, it's telling me how much data I have, how many bytes per row, how many data pages I need, how many dictionary pages I'm going to need, and my total data savings. So there's two numbers on this slide that are really important. You'll see at the top there, I've got a percent savings in data, 45%. My data, but as you can see from the numbers here, my data was wildly unrealistic in a very small sample set. Hopefully you'll see much better numbers if you're looking at production data. The other more interesting number possibly is the total percent savings when you consider the overhead of the dictionary. And again, because I had such a small sample of data, there's a significant difference between the 45% I saw in data rows and the 19% I saw total. If this were a billion row table space, those numbers would be identical. So what's the story on table space compression? The row is compressed and expanded by SQL. And the point of that is that all the SQL sees is the decompressed data, as if it had never been compressed. So this is purely a disk savings feature. Copies and logs are compressed because when an image copy is made of compressed data, obviously it's just copying the page images from disk or from the buffer pool, and those are compressed. Because the updates are reflecting the data on the page, which is compressed, that's all, the logs also are effectively compressed. The point of that is that if you run log and data analysis tools, they might run a little slower with the need to decompress the data to present it. I have very carefully referred to this as table space compression. And of course, one point of that is that index data is not compressed. Because the keys are decompressed, anything that extracts keys from the table might possibly be slowed down because of the need to decompress. Index processing is not slowed down. So one effect was of compression was to raise the interest for performance considerations in index-only access. And we've seen in large production shops, some indexes are bigger than their table spaces because of the effect of compression on the table. So the bottom line here is that this is a very effective technique to reduce disk usage without undue effect on your SQL applications. Generally speaking, if you're going to do access to compressed data, random access, and by that I mean access to a single row or possibly a very small number of rows, is generally going to show better performance than sequential access, where you're accessing a number of rows. And the reason for that is that you incur the compression and decompression overhead for each row in the set that you're referring to. So if you're actually processing 1 million rows, even if the result set ends up smaller than that, on a compressed table, you're going to have to decompress each of those to do any effective analysis of the contents in your SQL statement. So random access tends to be performed better than sequential access. I mentioned earlier that IBM has made changes to table space compression over the years, and these are the few that I wanted to call out. In DB2 IBM added a feature called auto compression. And all that means is that you can now build a dictionary without you running the load or reorg utility. When I talked about building the dictionary, I referred only to load and reorg. And at the time table space compression was first developed, that was true. Until you ran a load, you couldn't compress the data. Until you reorged it, you couldn't build a new dictionary and recompress it. As of version 10, the insert process can actually start to build a dictionary. In DB2 12, function level 504, IBM added Huffman compression. which is an extension to the existing table space compression. And we'll talk a lot more about that later. And in function level 509, this is very recent history, IBM added object level Huffman, which allows you to control Huffman compression at with your DDL at the table level. So normally I pause for questions, and I hope to be there in the room when this recorded presentation is read to answer them. But if you were to have any, please submit them to the moderator, and one way or another, I'll get a hold of them and try to answer them. And the reason for pausing for questions is that we're now going to discuss index compression. So this slide shows at a high level how index compression works. It's quite different from table space compression. The compression and the expansion is done at the time of I/O. So it's compressed on disk, and basically at any other time, you're looking at an expanded page. It's also done at the page level. The way that works is that the 8K, you must define a compressed index in the 8K, 16K, or 32K buffer pools, even though the actual pages on disk are always 4K. And we'll look a bit more at how that works later. As I said, compression occurs as each page is written to disk. So it's at the level of the entire page, and the data is expanded as you read it back from disk. Only the leaf pages are actually compressed. So even though non-leaf and root pages and system pages go through the algorithm, no compression actually occurs. The compression algorithm is performed in software. So basically it's squeezing out redundant information on index pages between consecutive keys and potentially in consecutive RIDs for a non-unique index. If you're going to read one key read pair off a page, the entire page must be decompressed. So that'll lead us to some different performance considerations than we saw for table space compression. Once again, the DSM-1 comp utility is available to give you an idea of what you might achieve by compressing an index. And again, the sysit1 DD points to the VSAM file in my example. In practice, you might want to take a DSM-1 copy or a copy of a copy yes index and use the image copy to avoid the need to deallocate the index from your production space. The only additional parameter applicable to running DSM-1 comp against an index is leaf lim. If you specify that in your parameter, that limits the number of leaf pages analyzed and allows you to get valid results without passing the entire index. This is obviously meant to allow you to get decent numbers for a very, very large index. So let's look at the output from an index DSM-1 comp run. I haven't shown it all for reasons of space, but you'll see in this case, the report evaluates compression with different index page sizes. So you get a report for what would you see if it were 8K, 16K, or 32K. In this case, we can see that with 8K, we're getting a 43% reduction in leaf page space. 12% of the buffer pool space would be unused to ensure the keys fit into the compressed buffers. So if you think about it, when Db2 goes to compress a leaf page on an index, there's two possibilities of how Db2 might decide that the page is full. One, you might not have enough room in the uncompressed image to fit the new entry or new RID in. But the other is there's room in the uncompressed image, but when you compress it, it will no longer compress to fit inside a 4K page. And that's basically what's happening here. So the point of all of that is that this is telling me that 8K would be the optimal page size for this. And we'll see a little bit more on the next page. You can see that the net reduction in leaf page size, or leaf page space, is about the same as what we saw for 8K. So if I give this, make this a 32K page buffer size, I'm just completely wasting 24K of each 32K page image. And notice that what was 12% of buffer pool space unused is now 77%. So again, the report has told me that if I wanted to compress this, I would need to use 8K page, an 8K buffer pool page size. So let's talk a little bit more about how pages are written to and read from the index and read and written to it. We can see on the left the different buffer pools. Blue is meant to be the 8K, yellow is 16, and red is 32. And they're all getting compressed into a special 4K buffer, which is not part of the buffer pools. It's page fixed in Db2 memory and used for the I/O between the disk and the decompression or compression algorithm. So going one way from, for example, the blue 8K pages, a page is compressed into a 4K image and then written out. Several pages are written out at a time to the potentially to the disk. Coming back, let's look at the second arrow on the right. A 4K page is written into the fixed buffer, page fixed buffer, expanded to 16K, and then written out to the buffer pool. So because all of the keys on an index page have to be decompressed or compressed at the same time, this means that you're paying the overhead for one row or one key entry or all the key entries on the page, which means that sequential access of a large number of index entries is generally speaking going to perform better because there's less overhead than random access for indexes. So this is the exact opposite of the situation we saw with table space compression. Because the pages are fixed, because the pages include more keys, they're compressed on disk, we tend to do fewer IOs. So you might see a performance improvement from that. Because we're doing fewer IOs and the pages in the intermediate buffer, the 4K buffer in my diagram, are fixed, there tends to be less CPU used. The CPU that is used appears as class 2 CPU for synchronous IO or DBM1 SRB time for asynchronous IO. So it typically is not credited to your thread. Usually at this point, I ask how many people in the audience use index compression, and in contrast to table space compression, a few times it's been no hands at all or possibly one or two. So this hasn't really caught on, I think, because of the CPU overhead that we tend to incur. Again, IBM has made one change to index compression since it was introduced in version 9, and that's in function level 500 of DB212. IBM added an online alter index compress yes. Prior to that, I could alter an index to compress yes, but the index went into reorg pending. So I had to rebuild or reorg the index to implement the compression, and that index was inaccessible until I did it. Now, with DB212, I can issue the same command. It puts it in AREORP, and users can continue to access it until the next reorg or reorg index is run. So this wasn't really an enhancement to index compression so much as an availability enhancement. Well, let's take a look at lob compression now. And again, we're going to see some similarities with the previous methods we've seen, but also significant differences. Like index compression, lob compression is done at the time of compression and expansion is done at the time of I/O. And there's a mistake on my slide here. That 4K on disk does not apply to lob compression. Basically, you can put the compressed lobs on any buffer pool size you want, 4K, 8K, 16K, or 32K. Unlike index compression, which is a software algorithm, the lob compression is actually exploiting an attached processor, the ZEDC. So it's similar to what we saw with table space compression in that because it's a hardware instruction that's being exploited, it tends to run significantly faster than trying to do it in software. Again, from the buffer pool outwards to SQL and everything that might, and the utilities, everything appears to be decompressed. As lobs are written to disk, they're compressed, and as they're read back in, they're decompressed. Let's look at that process a little more. The ZEDC was designed to provide compression of large files. And if you think about it, up to a 2 gig lob basically looks like a significantly large file. But it's not all compressed in one big chunk. It's compressed in 1 meg pieces. So in our example here, we're assuming a 32K lob value, which happens to be uncompressed, happens to be 2069K, which is 2 meg plus 21K. And I picked that size for a reason that we'll see in a minute. As it's written to disk, each 1 meg piece is compressed and written to hopefully a smaller number of pages. And in my example, the first 1 meg piece, the yellow piece, has been compressed to 513K. The blue 1 meg piece is compressed to 508K. And that leaves 21K, which is compressed. Oh, there's no point in compressing it because it's already less than a page. So in that case, the lob compression algorithm doesn't compress the page. So this is an example of one lob column value that's partially compressed and partially uncompressed on disk. So DB2 has to keep track of all of that and handle it when it's read in as well. If the entire lob were less than 32K, less than 1 page size, none of it is compressed and it's written out uncompressed. The values for the uncompressed and compressed length of each lob value are maintained on in the compressed space so that DB2 can look at the disk and figure out what his, how much space he's going to need when he decompresses. What do you need to implement lob compression? First thing is Db2 for ZOS, which shouldn't be a problem for anyone listening to me at this point. It's not available when you first migrate from V11 and bring up function level 100. It doesn't become available until you bring up M500, which is equivalent to new function mode. Even though we're talking about compressing the lob, the feature is only available for lobs on a UTS base. You obviously need the ZEDC chip, and I included what that stands for, Z Enterprise Data Compression. You need ZOS 2.1 plus PTFs or ZOS 2.2 or higher. Since we're now on 2.5, the current GA release, that shouldn't be an issue for anyone. The ZEDC has to be enabled, the hardware feature has to be enabled in the IFAP RDXX ParmLib member. And there's an example of one of those ParmLib members in the notes for this page. You have to be running on a Z12 or above with a licensed hardware feature for compression. I mention Apple Compat here because it's very important if you're interested in writing the DDL to set compress yes, either create or alter a lob with compress yes. You have to be bound at an Apple Compat with V12R1 M500 or higher. or the create command is going to fail because you haven't, you're running on an Apple compat that doesn't support that new SQL. The last note here is that Z compression is dictionaryless. The dictionaryless is in quotes because it really does use a dictionary. However, the dictionary for each compressed lob is stored in the compression stream. So effectively, there's no dictionary in the lob table space, which is the point of the point. So like index compression, you don't need a dictionary, and compression is done one row at a time as opposed to one page at a time. Again, our friend DSN1 comp is available. Again, I specify, in my example, I pointed to the lob table space, but you probably would want to point to an image copy. This run was against the lob based on a PBG table space, but I found you can also run DSN1 comp against the lob whose base is not a UTS. So one possible use of this is to look at spaces with lob columns that are candidates for conversion to UTS so that you compress the lob. So DSN1 comp will allow you to get that information in that case. You can also run it against a compressed lob to check the ongoing effectiveness of compression on your data. So what does the output look like when you run lob DSN1 comp against a compressed lob or a decompressed lob? First, it gives you some nice table space statistics. How many lobs are in the table space? What's the minimum and maximum size and the average? And you can see from this, again, that I have an absolutely pitiful sized lob. Hopefully, you're going to see much bigger numbers for your production values. One interesting fact is that there does seem to be quite a variance from 1 kilobyte to 8 meg in size, the average being 1.6 meg. So I've got quite a variance here in my size of my lob columns. This gives me the corresponding numbers to what we saw before. What percentage of data am I going to save if I compress this lob? And 56% is what this example shows. And I found for clobs that tended to be what we tend to see is about 50%. Just out of interest, I did try it on a typical blob, which included JPEGs. And IBM doesn't recommend doing this, but I did see a 10% reduction, further reduction. If you had an immense blob, it might actually be worth considering compressing it. For a 32K page size, it's telling me about the same amount. So like as with indexes, it'll tell you what different compression ratios you might see with different page sizes. In the case of a lob, that's typically not going to make a whole lot of difference. Another thing that's worth considering here, especially if you have a case like my example, where there's a serious, a huge range of possible values, including some, in my example, some 1 kilobyte lobs all the way up to 8 meg. You might want to consider actually inlining a lob to allow some of those smaller ones to be included in the base table and therefore compressed with it, as well as compressing the lob to handle some of the bigger values that you might want to get compression on. So something to consider. Okay, so I said I was going to talk about Huffman compression. And again, we've got a very familiar looking diagram. In fact, it's identical to the one for table space compression. And the reason for that is that even though Huffman's a little different, a different technique with different code, of course, to support it, operationally, it's exactly identical to the table space compression we've all been used to. Huffman compression was delivered as part of function level 504 of Db2 12 in March 2019. The Huffman advantages are basically, the advantage to using Huffman is basically they're taking advantage of hardware compression that was delivered with the Z14. The basic idea and the reason it's called Huffman is that the fixed 12-bit dictionary entries used for the libsimple algorithm can now be mapped to varying length bit strings. So more frequently referenced strings use fewer bits in the dictionary. So we now refer to the older compression technique as fixed length and the new one as Huffman. As I said, Huffman technique still depends upon a dictionary. It is a different format from that of the fixed length technique, and it is built in the same way, either during insert activity or by a load or reorg utility after you've created the compressed table space or done an alter. Again, the load utility works in a very similar way. It writes the overhead pages, starts writing out uncompressed rows, finishes the dictionary, writes it out to the pages of the table space, and then from then on writes compressed rows. So the dictionary management is exactly this, has the same considerations as we saw with the fixed length compressed tables. The same page set cannot contain both Huffman and fixed length rows. I think that's probably obvious because you can only have one dictionary in a table space, but it's probably worth saying. However, you could have different partitions of a partition space compressed using different techniques, some Huffman and some fixed. Again, DSM-1 comp is available to us. And the ability to show both fixed and Huffman encoding in DSM-1 comp was implemented in an IBM APAR PH19242. The PTF was UI 69388, and this APAR was closed on May 7th, 2020. The title is Enhanced DSM-1 Comp to provide compression ratio estimation for Huffman compression and provide comparison to existing fixed length compression. Part of the PTF added a new parameter to DSM-1 comp called comp type. I haven't shown that. It can be fixed, set to fixed or Huffman. I haven't shown it because in practice, it's easier to just leave it off. If the JCL is run on a Z14 or higher, DSM-1 comp will calculate the savings for both fixed length and compression, fixed length and Huffman compression. So we'll show that in our output on the next slide. I apologize for the formatting here. I really got squeezed for slide real estate. But you can see that the first couple of lines compare the percent savings for fixed, 45%, with the percent savings for Huffman, 39%. And again, this is a very small sample set, so I'm not sure how realistic that is. What we have seen in our testing is that we're not seeing, even with large potentially compressed spaces and frequently repeated strings in the table, which you'd think would be completely optimal for Huffman, we're not seeing very impressive increases in compression ratios. Obviously, if you saw these numbers in one of your production spaces, the decision would be to stay fixed and not use Huffman compression. Why do more work to save less space? So Huffman compression, the same considerations apply to it as to fixed length compression. Again, random access is probably going to, in general, be more effective than sequential access. CPU usage will probably be higher than for fixed, but the disk savings should be greater. In function level 504, IBM implemented the TS compression type ZPARM, which was set to either Huffman or fixed length. If you were to alter or create or reorg a compressed yes space at that point, the ZPARM would control whether you did fixed length or Huffman compression. In 509, function level 509, IBM added a lot of flexibility by supporting DDL. So you can now default it if you want by saying compress yes, and the Z-parm will still apply. But it seems much better to me to specify compressed fixed length or compressed Huffman. And so you can actually choose it space by space, partition by partition if you want to. So that's the end of my prepared slides. I'd like to try and summarize. We saw that compression, I hope, can be a useful data management technique, particularly table space compression. It served several production shops very well for well over 20 years. You do need to be careful. Remember Tonstoffel, there ain't no such thing as a free lunch. Analysis of the catalog fields and DSM-1 comp against selected spaces can be useful tools to help you determine how much value you're going to get out of potential compression. Be aware that compression isn't the same. Table space compression, index compression, and lob compression are all very different with different advantages, disadvantages, and operational characteristics. And I hope I've given you at least the basis and understanding of that. I hope this presentation has piqued people's interest. There's a lot of potential research you can do. Just playing with DSM-1 comp can be a lot of fun. So I highly encourage you to go out and check that. As I said earlier, if there are questions, I think you'll be able to submit them in the chat window as this presentation is the recording is being played. And I'll either be there at the time or I can try and answer them later. So in conclusion, I want to thank you all very much for listening to me. I hope this has been helpful. Thank you.
Well, thank you very much, everyone, for attending. This has been session 2AH. That was Jim D. Please leave your feedback, and please also remember that GSE this year are supporting, GSE this year are supporting the RLNI and guide dogs for the blind, and not blind dogs for the guides. So please fill in your feedback form. This is how we improve our stream sessions year on year. It was great to see so many of you attend. We've now got a little break, so I shall see you soon.